Hello everyone, and thank you for joining us today for the webinar From Manufacturing to Recycling, X-ray Technology and the Battery Life Cycle. My name is Michael Evans, and I'll be one of your hosts for today's webinar. So first of all, what is the battery life cycle? And for us, this represents all the different steps in the value chain required for manufacturing a commercial battery, starting from the raw materials, all the way through battery pack assembly, and finally to the recycling, where we want to we try to and want to recover all the valuable materials that are inside that battery, like lithium, cobalt, nickel, etc. So today's outline, we are going to introduce 3 different analytical techniques using X-rays and show some application examples of those. So starting with X-ray diffraction, followed by X-ray fluorescence spectroscopy, then X-ray microscopy, and finally at the end we'll have some time to answer any questions that you might have. Okay, great. So let's jump right in. I'll show you a few application examples using X-ray diffraction, and then we'll have a quick laboratory session where we can show this in live action. So what is X-ray diffraction? Well, it's an analytical technique that provides quantitative phase and structural information, and it allows for analyzing dynamic changes that occur within a battery during its operation. Nice thing about it, it's a non-destructive method. Sample preparation, measurement, analysis, all of these can be automated in certain situations. And we are sensitive to the crystalline phases and structural changes. So here, if we zoom in inside of a battery, we can see here the anode and cathode phases. We are sensitive then to the structural makeup of the electrodes. And here this just represents some different diffraction patterns and how we can see changes occurring within a battery during its operation. So the lineup of X-ray diffractometers offered by Bruker, we start all the way from, on the left-hand side, from benchtop systems. This is the D6 phaser, which is the most powerful benchtop XRD available on the market. From the D8 Endeavor, which is for process and quality control. And finally, the platform solutions, the D8 Advance and the D8 Discover, which are versatile, upgradable platform solutions for all of your analytical needs. Okay, so where does X-ray diffraction appear along the battery life cycle? And here I've just highlighted a few different applications, starting from the raw materials and precursors. I'll show an example of calcination monitoring, and an example as well for quality control of cathode active material powders, where we can do a structural analysis and get some very nice structural detail for quality control of these materials. And then a couple of examples where we look at different cell components and during the cell manufacturing. So including operando measurements on pouch cells or coin cells. And this is what we will show in more detail during the laboratory session a little bit later on. Okay, so the first example, this is spodumene phase transformation. So the naturally occurring alpha spodumene, this is a lithium-containing ore. So this has a very low reactivity. It doesn't dissolve in chemicals very well, and it's largely due to its compact structure. So it's since it's so compact, it's very difficult to extract the lithium ions from this material. But if you heat it up, it undergoes a phase transformation to this beta form. This has a larger, more porous structure. This has a higher reactivity, and it's far easier to extract the lithium ions from this phase. Now, with X-ray diffraction, we can nicely monitor what happens as this sample is heated. So we can see here, this is the diffraction pattern of the alpha spodumene. And as we heat the material up, eventually we start to see the formation of peaks from the beta phase. The peaks from the alpha phase disappear, and then eventually, once the calcination process is complete, we see that pure beta spodumene here is to be seen. The alpha form has disappeared. So this is nicely monitored using X-ray diffraction. Second example, this is a cathode active material powder quality control. So this is an example with NMC powder. And here we can do a structure refinement and extract some different quality parameters from that structure refinement, including things like the crystallite size, lithium-nickel anti-site defect. This can be quantified quite nicely. Also a C/A ratio. This gives an indication about the spacing between the layers. And a larger spacing has more room for the lithium atoms to transport in and out of the material. So this has a higher lithium ion diffusion rate. So at the bottom here, there's some analysis from different NMC powders. And we can see things like crystallite size. We get numbers here, 270 nanometers. This is something that's quite easily observable with X-ray diffraction. Above 1,000 nanometers, these numbers start to get a little suspect. This is rather on the limit or maybe even past the limit of what you're able to really see with X-ray diffraction. But we can see here this whole process. So you can automate from sample preparation, measurement, the evaluation, as well as the reporting. All of this can be nicely automated. Another example, this is graphite coated onto a copper electrode. And so one of the things that influences charging rates are the diffusion of lithium ions. Now, this can become quite slow when you have thick electrodes or when the lithium ions need to travel quite a long way in and out of the structure. So in this case here, we're representing graphite particles. So when the graphite particles are laying in such an orientation where the layers are parallel with the surface of the electrode, we see that the lithium ions have a longer way to travel to go in and out of the structure. Now, when the particles are oriented in such a way that the layers are now perpendicular with the surface of the electrode, now the pathway is far shorter, and the diffusion rates can be increased. And this is something that is nicely monitored with X-ray diffraction. We can see here on the right-hand side, this is the 004 peak of graphite on the left, and the 100 peak of graphite here. And so in this orientation, you see this ratio of peaks for graphite. Now, in a different orientation, if we were to have more particles oriented in this way, we would see that this peak from graphite would have a lower intensity, while this peak from graphite would have a higher intensity. So by monitoring the ratio of these two peaks, we get what is called an orientation index. And this gives us a nice indication about the orientation of the graphite particles on the surface of the electrode, and you can get a nice quality number for how the particles are sitting on the surface of the electrode. Last example, this is operando X-ray diffraction on battery cells. And here you can relate the battery performance to structural changes within the anode and the cathode. Here we support both pouch cell, let's say pouch cell geometries and coin cell geometries. Also, all solid state batteries can be nicely prepared inside of this battery cell here. Also nice here, we have a fully integrated software control, so you can really relate changes in the structure of the battery, of the materials in the battery, and directly correlate them to electrochemical data. So here, for example, we see here, this is the voltage curve throughout the charging and discharging cycle, and the diffraction data you can see here nicely, and relate the changes of the diffraction data to the electrochemical data. This is just a little bit more detail of the same example. This was an NMC 622 pouch cell cycle at a C/5 rate. A nice thing about a setup like this, with a large detector, you can collect a lot of diffraction data in one snapshot. You can do these snapshots very rapidly. This example was done at 3 minutes per snapshot, but it can be done much faster, 10 seconds, 30 seconds, something like that. You can get a lot more diffraction patterns, a lot more data if you want to do faster cycling experiments. And you can relate nicely here. We can see this is the quantitative amount in the anode. So for example, graphite turns into lithium carbon 12, and then finally lithium carbon 6. And then this process is reversible. We can nicely quantify the different anode phases here during the cycling process, as well as see nicely how the cathode, the structure of the cathode is changing during the cycling. And you can see here, this is the C lattice parameter of NMC. This relates to the distance between the layers in NMC. So this structure expands and contracts during the cycling process. So now I'll hand it over to Dennis, who's going to show this in a little bit more detail in the laboratory. So over to you, Dennis.
Hi, my name is Dennis. I'm working as an application scientist for Bruker. I mainly work in the topics of powder diffraction and battery applications, and I want to introduce you to a DIAD Advanced dedicated for battery research. Let's have a look. So in this system, I'm using a molybdenum tube on the primary side, which has a high intensity and a rather short wavelength compared to copper. This will allow us to catch more diffraction signals in a smaller 2 theta range. I'm using a focusing Göbel mirror as an optic, which will allow us to gain even more flux and a very high resolution. It's focusing towards the detector. I'm using some scatter protection in front of a pouch cell. Here I'm using a single layer pouch cell NMC that's briefly disconnected to have a look. So I can easily mount and unmount the sample. So default pouch cell mounted on a clamp. This clamp allows me to mount it reproducibly on the XYZ table. So here I can adjust the Z, X, and Y, but I typically don't need to adjust anything since the sample can be mounted in a very reproducible way. Let's connect the plugs again. First the plus pole, then the minus pole. And on the secondary side, I'm using an Eiger 2D detector to catch a large 2 theta range. We will be using it in a 1D mode to collect snapshots. This allows me to catch up to 20 degrees 2 theta in this configuration, but I can flexibly change the position of the detector, put it further away from a resolution, or put it closer to the sample to gain more 2 theta range. To charge and discharge the battery, I will be using an SP50 potentiostat, which will allow me to charge and discharge while I catch XRD scans. So here we will cycle the battery and continuously record XRD scans, which will allow us to have a look on the structural changes during the cycling experiment. We call that operando XRD, operando analysis. To show you how this is done, let's have a look at the software. In the commander, we can see the current settings of the tube and the drives. The tube is set at 2.25 kilowatts, and we can see the settings of the potentiostat. We see voltage and current. In the scan setup, we define which type of scan we want. We want to have a still scan so the detector doesn't move, and we are collecting data for about 10 seconds. Let's start this one. So the detector has an opening of 20 degrees 2 theta. We are catching the intensity from 7 to 27 degrees 2 theta. We can easily distinguish the NMC reflection, graphite reflection, aluminum and copper reflections, and a few more. And as you can see, the intensity and signal to noise ratio with a 10-second scan is completely sufficient to evaluate this data later on. To get this into a controlled state with the potentiostat, we are going to switch to the wizard. In the wizard, we see the Da Vinci, where we have all the information about our system, the molybdenum tube, the Eiger detector, electrochemical cell, and all the other parts are recognized. In the XRD setup, we define the type of scan that we want to have, which we already defined before in the commander, still scan at 17 degrees 2 theta for 10 seconds. And we're going to use that in the multi-technique table editor, where first of all, we define different modes for the potentiostat, for example, constant current charging for at 18 milliamp until we reach 4.2 volt. And then here we have a measurement attached with a repeat option, which means this measurement is repeated until this potentiostat step is finished. And it will go into the next step, holding constant voltage, and then the next step, discharge, constant current at minus 18 milliamp. So we will have a direct correlation between XRD scan and potentiostat values. Starting this will then look something like this in the end. We start the measurement and we will see how the data is collected here. And this will be performed completely automatically by the system with a controlled setup of potentiostat and XRD. The result will then look something like this. We see the aluminum and copper peaks not shifting their position. On the other hand, NMC and graphite peaks shift quite drastically, forming LIC12 and LIC6. Since this view is not that pretty, let's create something which is a bit easier to understand with a 2D view, which will help us to plot the voltage values against an actual change of the patterns. Let's change the color to rainbow. Let's change the scaling a little bit. And here we can now easily see what is happening with the NMC, what is happening with the graphite peaks. And of course, since we collected all of that information, we can plot in the side view the mean voltage for every scan. You can see nicely the charge and discharge curve. And if we are curious about a scan in this voltage here, we just click here. The appropriate scan is selected in the list, and we can create a 1D view for this singular scan. So this would be the scan at, let's check, 3.9 volts. And this is the result that we get in the end. I hope you enjoyed this demonstration, and if you have any questions, feel free to come back to us. Thank you.
Yeah, thank you, Michael. So my name is Adrian Fiege, and I will now take you through the second part of today's event, and this will be about elemental analysis with XRF in the battery life cycle, and we will close the session with a small lab session. So let's dive right into. So X-ray fluorescence enables, first of all, fast and accurate elemental analysis in all kinds of solid and liquid and powder materials. We can measure elements starting from boron even up to americium. In batteries, that means we typically start at fluorine and go up to uranium if you want so. In terms of elemental concentrations, we typically start at ppm, parts per million, and go up to 100%. The beauty here is that this can be done in one method, so without further dilution, for example. And in some cases, we can even go to sub-ppm ratios. XRF, so X-ray fluorescence, is being used in the battery life cycle in 3 different segments. So this is the raw material assessment, where we do incoming goods inspections, for example, the precursors, so liquid precursors, hydroxide precursors, and cathode active material. And there, also in the recycling, we are playing an important role. I will go into that a little later. One question that is typically asked when choosing the technology for your analytical needs is how much sample preparation is needed. For X-ray fluorescence, this really depends on the application, and with that, mostly on the sample type, of course. So we can measure all kinds of materials like metal foils, graphite powder, hydroxide powders, liquids, etc. And for example, liquids we would measure straight away in a liquid cup like this one. Preparation of such a liquid cup takes a few seconds, loading of the material another few seconds. You can measure this liquid within less than a minute, and then the analysis takes another few minutes. So this is really quick and easy also for powders. You can press a powder into a pellet that looks like this, for example. This is advantageous, especially maybe if you grind the material, you make it a bit more homogeneous. It's also relatively straightforward, takes a few minutes to grind and press the material. It means that you don't have a polymer foil at the bottom, which you have here, which absorbs the very light elements intensity. And for example, such a press pellet would be used if you measure fluorine in some of your materials. We can measure solids like metal pieces right away. Some might require polishing. Foils, such as aluminum foil, can be measured with XRF also in special filter holders. And last but not least, one preparation method that you often come across in X-ray fluorescence is the fused bead preparation method. Here, the sample is being fused into a glass bead with a flux. This gets rid of any heterogeneities and also essentially of the matrix, which can be disturbing. It results in very high accuracy and precision for major and minor elements. However, this is more something that you would see in mining and less common in battery applications. What are the actual benefits of XRF? Well, for that, we first need to look into the alternative methods, which is in this case also often cases the reference method, so the secondary method. And that is ICP, OES, and MS. So for ICP, OES, and MS, we have a couple downsides which we can overcome with XRF. One of them is with XRF, we don't need to recalibrate every day. We actually don't need to recalibrate for a very long time. And we can extend calibrations even if we want so. So this really enables 24/7 operation, even fully automated operation, which is not possible with an ICP where you need to recalibrate daily. We have overall a much shorter time to results. So this includes sampling, sample preparation, measurement, results. And this is especially true for powders and solids and granulates, where we don't have to dissolve the sample in acid digestion. We don't have to dilute the sample. We can maybe mill the sample or press the sample, like I said, and then measure it immediately. So this really reduces the time to result. Overall, it's also much easier to use, so we don't need sophisticated training or laboratory environment. We're also not dealing with hazardous consumables or expensive consumables. So this reduces the overall operational costs, including potentially also the labor costs. And last but not least, a nice point of XRF versus ICP, OES, MS is also the standardless solution. So you don't need to calibrate for everything. So for instance, raw materials can be nicely measured with so-called standardless programs, which use fundamental parameters. But now let's dive into some example. And one of the main use cases for XRF in the battery manufacturing is along the cathode active material preparation. Here we have different cathode active materials, of course. One of the most common ones is the lithium NMC, so nickel, manganese, cobalt in different ratios. Here we start with a sulfate salt and then a sulfate solution, preparing the mixture and a co-precipitation. So XRF here is already used for the salts, for the solutions, and especially the solution mixtures, where we would check if everything on the elemental side is fine, if you have the right ratios and the right purity. Later on, we can measure the recovered solvent for process control. We can measure the hydroxide precursor. Again, we would look into metal ratios and purity. And last but not least, we can, of course, also measure the cathode active material. I will show you a few examples of such measurements, starting here with liquid precursor analysis. In this case, we calibrated our energy dispersive system, the S2 Puma Series 2, with solutions, with sulfate solutions, so nickel, manganese, cobalt. And then we basically tested the calibration with a repeatability test. So here what you need to know is we basically measure that in air mode. We pipette simply the material into a liquid cup, as shown here, and then we load it into the material. It can also be handled, of course, by an auto changer, auto loader. And overall, you can say that the time to result here is on the order, depending on how fast you are with the preparation, between 3 and 4 minutes. Here we can see the results of a repeatability test, really extraordinarily stable for a long time of measurements for nickel, manganese, cobalt, far below 1% relative uncertainty here with 1 sigma, and even the 3 sigma is really impressive. Another example I wanted to bring to you is really the final cathode active material. That here, what we've done, we basically acquired a few cathodes active materials that are available on the market, so different NMCs, but also NCAs. These can be all correlated as pressed pellets on one calibration. So the material, which looks approximately like this, is briefly ground and pressed into a pellet, and then measured in our systems. We use the nominal values for nickel, cobalt, manganese, but also for the traces of aluminum, sulfur, and zinc. And then we used one sample as an unknown. It was an 811. We are pretty close. It's normal that they are never completely accurate. That is a simple production uncertainty. But what you can see here, that the measurements are really precise. I mean, we are far below, again, for the major constituents, below 1 and even mostly below 0.1% relative variation. And also for the traces, it's a quite precise analysis. Now let's switch to another key application, and that is recycling. First of all, a few words about the recycling process for batteries, and here this is focused on, again, on lithium NMC batteries. So there we would have a battery disassembly first, getting everything out that we can recycle separately, like the casing, for example. Then we would shred the material under a sort of inert atmosphere because it's quite reactive. And after that shredding, we will have a so-called black mass that then needs to go into a hydrothermal treatment where we basically separate then the metals of interest like nickel and lithium. XRF can help here quite a lot, and that is in the so-called black mass analysis. So we basically measure the metal contents like nickel, cobalt, manganese, and also various contaminants, which include fluorine, aluminum, and copper, for example. So we measure the black mass purity, and this helps, for example, to monitor and optimize the recycling processes. It is also used for value determination, so for those producing the black mass and selling it, and for those receiving it, it's also used for value determination. And then, very important here, one of the applications is we need to analyze this black mass before we throw it into the hydrometallurgical process. Why is that? Because we need to optimize our process so to be most efficient, cost efficient also, to get all these valuable metals out. Oftentimes in a recycling process you would calibrate. In some cases when you don't know what you're receiving, for example on receiving goods, you can use our standardless method which is called SmartQuant. So overall here, very brief summary of the applications of XRF along the battery life cycle. This includes mainly raw materials. I didn't touch everything today. We can also measure graphite, aluminum, and copper foil, for example. A major application segment is in the part of precursors, starting with the liquid precursors, going down to the final cathode active material, and even solvent recovery analysis. And finally, I talked about recycling applications. That's the black mass. So without further words now, I want to switch over to the lab, where Renata will show you and tell you more about our S2 Puma Series 2 here. Thank you, and see you later at the Q&A.
Hello and welcome to our XRF lab here in Karlsruhe, Germany. Thank you, Adrian. My name is Renata Janic. I'm an application scientist for XRF, and today I would like to show you how easy and fast XRF can be used for different kinds of battery applications. So here, this is our S2 Puma, our energy dispersive tabletop system, which can be used for this kind of applications. Typical materials which are analyzed by XRF are powders like NMC powders or black mass, but also liquid precursors can be very easily and fast analyzed with the system. Now I would like to show you how really fast and easy it is. So for powder samples or liquid samples, typically we use these liquid caps. They can be prepared by your own, or you can buy them ready to use. You just transfer the sample material into the cap. So I will do so. There is a lid, close the sample, and the sample is already ready to be analyzed. So let's have a look into the system. So this is the loader area. So the sample is just set into position. Here you can load different kinds of samples. So powder samples or liquid samples are analyzed in this liquid cup. So typically the elements are quite heavy, like copper or nickel or manganese. So you can run the samples under air mode. The same for the powders. Typically, you will also prepare a pressed pellet. So in case you want to analyze lighter elements, but for example also fluorine, then you can prepare the pressed pellets. In this case, you will just use 8 or 9 grams of original material. You will mix it with a binder, 1 or 2 grams of wax, and you will prepare this pressed pellet with a press. The sample is loaded. In case of very light elements or low concentration of light elements, or like also fluoride. In this case, we would typically use the vacuum mode. But also for the pressed pellets, for heavy elements, you can run the samples under air mode. The samples are loaded in this area here. There is a grabber. The grabber will pick up the sample and will load it into the measurement position. As long as the sample is running, you can open and close the lid, you can load and unload samples, so this is a very flexible system. Let's create a sample. This system is equipped with a touchscreen, so it's very easy to use it by different operators with really only a little bit of training. So you will just create the sample position. You can have different buttons here for different kind of methods like blackness, precursors. So I will just select one. You will type in the sample name. There's also the possibility to use the barcode scanner. You can also add additional information which are important for you, and the sample is already created, and you will just start the green start button here. Sorry, push the start button here. After the sample is finished, like this one here, the results are shown on the touchscreen. You can have specifications. So here I created one which is out of spec, so it's displayed in red. So the user immediately knows that something is not okay with this measurement. So this is all I would like to show you today. So please enjoy the webinar. In case you want to learn more about XRF and about battery applications with XRF, please feel free to contact us. Enjoy. Let's go back to the studio.
Welcome. My name is Geert van Holland, and in the last section of today's webinar, I'm going to show you some applications of X-ray microscopy along the battery life cycle. X-ray microscopy is an imaging technique based on microcomputed tomography, which you may know from the hospital. Like in medical CT, also with XRM, we can retrieve the 3D internal structure of an object. And to that purpose, we are actually rotating the object over 360 degrees and collecting hundreds to thousands of 2D projection images that are then mathematically reconstructed together. And because X-rays passing through an object are attenuated selectively, we actually are mapping here the local attenuation coefficient in the object. And that's then digitized in an 8-bit or 16-bit grayscale image. And by convention, the phase with the highest density is shown as white. In this AA battery, for example, that's the brass spin here. Yeah. Whereas the lowest dense phase, which is typically air, like for example in these pores that you see here in the zinc powder over here, yeah, these pores are shown in black. And phases with an intermediate density are shown as shades of gray. And that actually enables us to selectively visualize individual components or areas in an object. And then also to perform more advanced quantitative analysis. Like, for example, in this AA battery here, we can do a size analysis of the void space in the zinc powder, which is here color-coded to size. Medical CTs are very big systems and have a moderate resolution of something like 0.5 millimeter at best. With X-ray microscopes, we get down to micron resolution, and that's already possible with benchtop systems. Yeah? And even can go one step further with special designs and dedicated X-ray components completely decoupled from external vibrations. We can even achieve with systems like SkyScan 2214 sub-micron resolution down to 400, 500 nanometers. Features at these length scales, micron, sub-micron length scales, are really affecting the properties of a battery. And if we focus on the battery life cycle here, and we look here for with precursors, cell components, cell manufacture or assemble battery cells, there are several relevant parameters, like, for example, particle size, the shape of particles. You can do a foreign particle inspection, for example, in graphite anodes. You can evaluate in composite anodes, for example, the silicon oxide volume, the distribution of it. In the cathodes, the assembled cathode here, you can look at binder migration that's happening. Or later on, in completely assembled battery cells, you can really look for delaminations that are happening. You can assess the impact, for example, of a nail puncture test without having to section the battery that otherwise would also modify the structure of the battery. I'm going to show you now some real-life examples to illustrate this a bit more in detail. The first example is an NMC cathode powder that was sticked to a carbon rod just to separate the particles a little bit. You see in the center the 2D projection image, and next to it a slice of the 3D reconstructed volume. Well, you see indeed the high-dense NMC powders. Then finally here we do, on the rendered module, on the rendered model, we can do a complete evaluation of the particle size. And that's indeed partially also color-coded here, highlighted with this color coding here. So large particles in blue, whereas smaller particles are in green or even in red. And we get a complete distribution here of the particle size. Now that's something that's typically done with light microscopy or laser scattering. XRM, in this case, gives some additional information because you really get the 3D size and shape of the individual particles. And already in this experiment, these are more than 50,000 particles that are individually characterized without making any assumptions on the shape model, like, for example, in laser scattering. In addition, you can also get information about potential defects inside the particles. And that is relevant because these defects inside particles can later on, when you are calendering your cathode, can result in cracking of the particles. And that's an example I want to show you now. We've now casted the cathode particles onto an aluminium foil. You see here the sample. There's about a 1 centimeter foil over here, with the cathode particles casted on both sides of the aluminium current collector. So you see here 3 cross-sections of that sample. And when we now make a cross-section here along the green line, you get a beautiful 4K by 4K two-dimensional cross-section on the left, showing really in detail that you have, when we zoom in a little bit more, you see here very nicely cracked particles, indeed several cracked particles. You see also particles having a defects over here. You see also how compact the particles are, what's the void space in between. That's also relevant later on for the particle-to-particle contact areas, really important for the final performance in the end of a battery. And that's something you can qualitatively assess from these high-quality images. We can also do a more quantitative analysis, and to that purpose we have segmented here and rendered also the cathode particles selectively. So we've left out the aluminium foil. And then you can do again, like for the powder sample I showed you before, you can do here a complete quantitative analysis of the individual particles, and you can even color code that to also guide the eye to show you where there's maybe an inhomogeneous distribution of sizes, how that looks, how that is distributed into the 3D volume. And that's for a cathode example. I have also an anode example here, graphite on a copper current collector. That's for X-rays, always a little bit more challenging, because here you have a low dense phase, the graphite, on top of a high dense copper foil. That's always a little bit challenging, but nevertheless you see here very, very detailed information. And for example, you see already in this cross section over here that there are, for example, high density particles in the graphite layer. And you could do some foreign particle inspection, have this also as a quality control criterion in your production to count the number of particles above a certain size. In addition, you see here also very nicely that the current, the copper foil really has a rough surface. But looking a bit more into details, and in different areas, you see also that the structure of the graphite anode is changing from the foil towards the outside. So close to the copper foil, you have a pretty compact structure with small particles, also very compact, not too much voids. But when you move towards the outside of the anode, you see that particles become bigger and also the void space is increasing. And again, this qualitatively you get this feeling, but you can also quantitatively assess this. And that's what we have done here for the void space. So we've color-coded the voids in this rendered model in blue, and we've then made a complete quantitative evaluation and plotted this here. So we're actually moving here from the front side of the sample towards the back. And that's what you see here. So the void space, indeed, at the outside of sample A is very high, and towards the copper foil, the void space is reducing close to zero, and is again increasing again, going to the back of the sample. That's a quantitative analysis that you can perform here. And this is relevant because this, for example, is impacting parameters like tortuosity. Moving now to complete assembled cells. First of all, you can do a qualitative inspection of the cell design. There you don't need very high resolution, but you can still see very, very fine details. For example, here in this pouch cell, in the central example, you see, for example, that the layers here are a bit disarranged in the central area over here. But zooming in even a bit more and looking here at the cross-section, where the green line is, that's actually what you see here at the top, this is the cross-section. You see in this area that there are also locally more defects around that area. And that's something that's even more clear on this cylindrical cell on my right-hand side, where you see on the upper quadrant here, that's a very nice structure. So you see in white the electrode mesh and the separator. That's a very nice structure. But when we look here to the lower left quadrant here and we zoom in this area, you really see a lot of cracks appearing. And this is something, of course, later on that can make then issues, give rise to shortcuts, for example, and lead to early battery dying. Qualitative inspection. But again, here we can take this one step further, and let's take this example here of this lithium manganese cylindrical cell. And what we have done here is really evaluate quantitatively the structure thickness of both the separator in blue, color-coded in blue, and the the electrode mesh on the right-hand side. And you see indeed, the mesh, of course, is very well-defined structure. You see that is about 100 micron in size, very sharp, whereas the separator, of course, is a bit more uneven. You have these cracks, so you have a broader distribution, is also thicker. So you can quantitatively assess that structure. Another example is a 21700 lithium ion cell, cylindrical cell. And in this type of lithium ion cells, you have always anodes are longer than the cathodes. That's an important parameter because it has an impact on the capacity, that also has an impact on lithium plating. So it's very important to know this so-called anode overhang. It's not only the length of the overhang that is relevant, but also, for example, tilting. So if these layers are tilted here, they may touch each other and at some point give rise to, again, shortcuts. And that's something that can be quantitatively assessed, the tilt angle as well as the length, and plotted. So that is quantitative inspection of cells at the micron level. But even on battery cells, we can do more advanced inspection and characterization of the structure, and even at different length scales. So this is an example of a small pouch cell that's used in smartwatches, for example. And you can, like in the previous examples, you can get an overview by using a large detector, scanning it at several microns, but you get a good overview of the complete structure. You can also define your regions of interest, and then with different detectors, increasing the resolution at each step. For example, switching one detector, you already get here a very good overview of the anode overhang. Also, the tilt angle is very well seen. By increasing the resolution even further, you can see very well the different layers. And by using the highest resolution detector, you really get a very fine structural view of the different layers inside this small battery cell. For example, here you very nicely see the separators here. You see between the graphite and the cathode, and you see here also very nicely the fine structure of the cathode. And that's again something that you then can segment. Yeah, you have here done an individual segmentation of that single cathode layer, and again there you can then do a quantitative analysis. And to show you how this really works in real life, I will end this session with a video that picks up this example. And actually, the pouch cell was scanned on on SkyScan 2214. And first we do an overview scan with the large detector, moving the sample a little bit closer, and then collecting at different angles, around 360 degrees, different 2D projection images that are then mathematically reconstructed into a 3D volume. And here you see the rendered model. And like in medical CT, you can now move this object. You can virtually cut through this object, and you can, for example, inspect the layer arrangement. You can inspect the tabs. You can inspect the electrodes. You can also define here regions of interest. And then later on, with higher resolution detectors, do a more detailed inspection of that area. And that's what's happening here. So now we're switching to another detector, just a single click of a button in the software. We move the sample a little bit closer to enhance the magnification, so to have a better resolution. And then we're collecting 2D projection images again and get a very nice view of the structure, where you see here the individual cathode layers already, but also very nicely the longer anode foils. You see some of them are a little bit more tilted. And here you could then do, for example, a detailed analysis of the anode overhang, for example. And now by zooming in even more with high resolution cameras, you can start resolving the structure of the individual layers. Yeah. Like it is done here, you can move and inspect different areas. And then you can start segmenting particles and do a quantitative analysis. And to make that a bit more visual, you can color code these particles according to size and get a complete particle size distribution of this cathode layer and reveal the smallest details. And with that, we're switching scenes now and moving on to the Q&A session.
Yeah, thank you, Geert. And here we are at the Q&A session, all lined up. And I believe we already have a lot of questions, Michael, right?
Yes. So first of all, thank you everyone for sending in your questions. We won't be able to get to everything during this short Q&A session, but we'll try to answer as many as we can, and perhaps even afterward we can send out a Q&A document with some of the most relevant questions, and we'll try to answer those as best we can. So maybe first things first, this has been asked a few times. Are we going to provide a recording of the video to everyone?
Yes, we will do that. You will also get the slides, and like we just committed, we will also send some, most relevant FAQs.
Yes, exactly. So first question, how about, so you can say a little bit about accuracy of XRF analysis. What sort of relative errors can be expected?
Yeah. So XRF is a comparative technique. So you would calibrate, and most of the times, in terms of in batteries, battery applications, you would calibrate with ICP OES or MS as a secondary reference. Once you've calibrated, system is ready to work for a long time. It can basically achieve for most of the elements of interest the same precision as the reference method. That means for most elements the relative precision is less than 1%. For like the nickel, manganese, cobalt, it can be far lower, as you've also seen in some of the presentations, so even below 0.1% relative uncertainty.
Okay, great. So there's been a few questions about the resolution in XRM. And first, there's a question about what's the resolution of the battery particle XRM scan shown at the end? You have that?
At the very end.
The very end.
Yeah, the very end, if I remember correctly, that was something like 900 nanometers pixel size. So basically, we're there about a bit above 1 micron spatial resolution. Resolution is always several effects that come into play. On the one hand, there's the instrument, focal spot size. There's also the pixel size, the distances, and of course then also the sample size. Because using geometric magnification, so the closer you can get to the X-ray source, the better the magnification is. And in the benchtop systems that I showed in the lineup, basically I can go down to a few microns spatial resolution on small samples. The bigger the samples become, of course, then the resolution decreases. Let's say, the SkyScan 2214, the largest system, is going even sub-micron in terms of resolution. There you can really achieve 500 nanometers, 500 nanometers spatial resolution even, because yeah, it's a lot of care is taken in terms of eliminating vibrations from the environment, very fine spot size, high resolution cameras, so that definitely then helps also to really get down to this sub-micron resolution.
Okay. There's a question, I guess this one's for me, what about temperature sensitivity of you during operando cycling testing? Will the temperature affect the results during a XRD experiment? Yes, it can, and we recently learned that this can have a rather large effect, even just small temperature differences. So this is something that can have quite an effect on the performance of a battery, and I think we'll probably see this at every level.
Mm-hmm.
The temperature and what sort of condition history of a battery, for example, and that has quite large effects. Okay, let's see here. There was a question about reference materials for XRF analysis for batteries. Can you say anything about that?
Yeah, so there are not many certified reference materials yet. Actually, it's very few, and for the final cathode active material, so about battery-specific materials. So there's a lot of reference materials, for instance, when it's about pure metals, for example, the aluminum foil or copper foil. That's a different story. But for battery-specific materials, there's much less. Part of that is also that they differ from plant to plant, and normally what you would do is you either approach it with a standardless fundamental parameter approach, or you calibrate with secondary reference materials, because then you're closest to your process. So there's also a particle size effect on that. You can get around that with some grinding, but especially if you want to measure the powder, it makes sense to use your material from your process as a calibrating matter. Yeah,
I think that's a really important topic. I think we
can also expect that more and more standards will come in the future.
Yeah,
exactly. Yeah,
I think that will definitely come. I lost my place here. Yes, there was a question about lithium plating, and if that's something that we can observe. That's a really tough question, I think.
Yeah, it's a tough question. I do see some chances to see it with XRM, because the plating is normally happening in the anode, so the graphite anode. And maybe from the contrast, let's say between the lithium and the graphite, it's not much, but maybe it's sufficient to indeed see that if it is, let's say, yeah, you have at least some plating, not when it's just starting maybe, but with XRM maybe from contrast you may be able to see that. Yeah.
It's so tricky. Yeah.
It could be. I mean, if it is really elemental lithium, perhaps there is something to be seen in an XRD scan as well if it's crystalline. But it'll depend on how much, and usually because lithium is so light, it's not the best element for X-rays. We struggle with lithium. Right. So there were a few questions about sample preparation, particularly for XRF analysis. Can you say a few words about sample prep?
Yeah. So generally speaking, compared to other elemental analysis techniques, the limited amount of sample preparation that you need is maybe one, if maybe not the biggest advantage of XRF, especially also in batteries where you could measure the liquids, the powders as they are. However, especially in battery recycling, you would also look into electrolyte residual, and one indicator for that is the fluorine content here. And this measuring the fluorine is only possible without a foil at the bottom, so without a polymer foil at the bottom. So in this case, you would press the material into a pressed pellet, and oftentimes it is also beneficial to grind it before. So there are industrial type grinding machines for XRF and also XRD applications, which can be used here, and also presses, and they are pretty straightforward. So the preparation here is easy, highly reproducible, and you can do it in a few minutes. So
yeah, with XRD, sample prep is also an issue. It's not quite as critical as it is for XRF. But there are some ways, especially for in a quality control environment, to have an automated sample preparation for XRD, for XRF as well. So this can be quite useful, quite important.
For XRM, maybe to add here, that in principle it's non-destructive. But of course, if you really want to achieve the highest resolution, you sometimes need to cut down a sample to really get to this sub-micron resolution. That is the limiting factor. In principle, it's non-destructive.
I'm glad you mentioned that again, because there are a lot of questions about resolution with XRM, and that's quite critical. It really comes down to sample size.
Exactly. Yeah.
Okay, so there was a couple of questions about is it possible to do operando experiments on older XRD systems? I mean, short answer is yes. You can certainly do that. Then typically the experiment would be done manually. So you would be controlling the electrochemical data and settings independently from the diffractometer. Then you'd somehow have to relate those two parameters later on with the scans. One of the benefits with the newer systems is having a full integration of potentiostat along with the diffractometer. Then you can really control both the electrochemical experiment and the X-ray diffraction experiment, couple those two together, and then you have everything in one. But certainly those experiments are possible in older systems. Just wouldn't have the latest technology available to you. Right. Okay. Recycling. Okay. What can you say about recycling? We've had a couple of questions about recycling, and I think it may be good to go over that a little bit more.
Yeah. I mean, recycling is first of all a topic that's all around us, especially also in those regions which are now like ramping up, like in the US and in Europe, also because of many of the resources are critical. The problem is, one challenge is that you're dealing with a lot of material around, so there's always this disassembling, and at some point, currently the only real technology to do this is shredding. You need to do this under an inert atmosphere, and at some point, okay, you can get some of the aluminum casing that's to separate is relatively easy. But at some point, to really get especially the high value materials, it's the lithium, the cobalt, and the nickel out of the material, you are down to a hydrometallurgical process. And so here, XRF especially can play a role to measure that so-called black mass that you have then after the more mechanical part before you go into the hydrometeorological part. And it can then differentiate on the one level between to make sure that you have type pure materials. And it can then also allow to make sure what you throw into the hydrothermal hydrometeorological process is what you expect. Because to make that relatively, let's say, cost and energy and material efficient, you need to know what you're throwing inside. So here, XRF can support a lot. We often get the question whether we can also sort. That's not really a topic here. So the sorting is still something that our technologies typically can't do. Yeah, so that's something you need to do more upfront. Yeah.
It's going to be a really important topic because now the chemists are coming up with all these different different ways and different chemistry, different formulas for batteries, and that's just going to cause a bigger and bigger challenge for recycling companies.
Yeah.
Okay, so I think we're just about out of time. So there's a few questions we didn't get a chance to get to. I apologize for that, but we'll try to answer them at a later time. And there was also questions about getting a copy of the presentation. We will certainly send that around as well. So we'll send you a copy of the slides and a copy of the recording. So you have that. You can watch again at your own leisure. So I think we can wrap it up.
Yeah, I think so. So thank you very much for your time, for tuning in today, and yeah, have a great rest of your day.
So
thank you very much.
Thanks for joining.
See you then.
Bye-bye.
Bye-bye.